comparison of Norway and Switzerland. We can see all of the things we could see before for both of these distributions. So we can do something of a comparison between the two. I mean, obviously, Norway seems to have smaller mountains in this database than Switzerland does. The center is much lower. The range doesn't go quite as high. But the shapes are kind of similar. They both have this roughly normal shape, flat in the center and two even symmetric tails on either side, based off the vertical lines and the flat line. Interpretive dance a little bit there. We can also do the same thing with the histograms. For comparing two distributions, this is actually one of the reasons why I prefer a quantile plot. I find this easier to read than trying to interpret this histogram. Mostly because with this histogram, if I want to interpret one spot compared to another spot, I need to choose one point, look at the height, and try and go along these non-aligned axes. Do the same thing with the kernel density estimate. Once again, best looking of the three plots in my opinion, and I think in the opinion of most people. It looks the fanciest, like nice smooth curves. Who doesn't like that? I've dropped the ash estimate because I don't want to do that more. Labeling also becomes way more important than with an individual one. You can kind of figure out what's going on with a single plot as long as you have the title. But when you're doing two different plots, it needs to be obvious which one you're looking at. But there are some problems with this. So there's kind of this idea of wasted space. If we go back to something like the quantile plot in particular, most of what I've put there is just blank white space. When you're trying to read this, you're visually going over a whole great distance to compare these two curves. The other problem with this is you can't compare parts directly. Like I said, for the histogram, you need to look at one part and then look over at the other part. And while it's a pretty simple eye movement, sometimes it takes a bit of extra focus, takes a bit of extra thought, and that just makes it a little bit harder to read what's going on. The other problem is order. So if you're at all familiar with this idea of anchoring, when you're given something and then something else, the way the first thing is presented is going to affect your perception of the second thing. There's actually a really fun experiment that Wayne does for this in his exploratory data analysis course. I don't know how many of you are taking that next semester. But in that course, he asked people like the height of the tallest tree. And for anyone taking it, just answer honestly, but the number they're given affects the height they guess. It just screwed up that experiment for him because anyone going into it knowing that is going to be aware of the anchoring effect. So, given that there's all these problems with side-by-side displays, we could try overplotting and just add some colors to distinguish between the different distributions. So here we have overplotted quantile plots. I've added a little legend there so that the reader can actually see what's going on, know which country is which. And here, the difference in the height of the Swiss peaks and the Norwegian peaks is pretty obvious. There's obviously a way higher center to those Swiss peaks, and even the lowest peaks in Switzerland are relatively high compared to the lowest peaks in Norway. It works pretty well for the kernel density estimate, but already there's kind of this problem you might see here. I've used alpha blending here, which is to say the colors I'm plotting have some transparency. You can see through them, so when you stack them up, rather than just obscuring each other, they kind of add together. But when you do that, you kind of get this problem with perception where, at least when I look at this, I don't see two overlaid densities. I kind of see three distinct regions because the color in that middle region has changed. For me as well, the brighter areas, that is the areas which aren't overlapping, pop way more than the darker area. So there's this unintended visual consequence of doing this overlaid plot. And I think it's even worse for a histogram because you have these straight lines. Whereas with the density, there's kind of these nice curves. Here you have these bars, which are clearly delineated. And because you're trying to read these bars, you're kind of attuned to looking for the height. And so for me, for example, all of these bright red ones right here really draw my eye away from the pattern. And I don't really view it as one continuous density as so much three regions. Like I say here, it appears like different stuff. So while this overlay plot works really well for quantiles, you color them, you get these two lines, it's really easy to compare them. Maybe it doesn't work so well for these density estimates. Like I said, part of the difficulty is this alpha blending. It's necessary, otherwise you wouldn't be able to see behind one distribution. But there's a consequence to this necessity. And This is just going through what I talked about in a little more detail for anyone who wants to read this after the fact. But when you're using a density estimate, we actually can avoid this by using back-to-back plotting. I believe they're called like fiddle plots if you look them up for density estimates in particular. Or I think it's demographic population pyramids in the slides that are the main way you look at this. This requires a little bit of code. You can see here I've written out in detail how to make this back-to-back histogram. Same thing with the density. It's a little bit easier with the density. With the histogram, because the histogram is recorded as breaks, you essentially need to construct a bunch of rectangles that go horizontally rather than vertically. This is what R does in the background when you call the hist function. But for the density, all you need to do is swap the x and y when you call the polygon. And then it does all the work for you. Once again, adding color. And I think personally, this is a lot easier to compare. You can kind of do a direct comparison of these aligned lengths. Or at the very least, they're all aligned on the vertical axis. So there's a direct comparison side by side, and you have no weird visual effects where the colors cross over. The only thing that is a problem with this is you can't actually do more than 2 distributions back to back. That should be obvious. But as you're moving up to comparing more and more samples, overplotting, you can accommodate as many as you want. It'll become a complete mess, totally unreadable, but you can do it. But there's no way to actually do that with a back-to-back plot. It only works for comparing 2 samples, which might be good enough. When you're going up to higher samples, I believe actually this is in tomorrow's lecture, way better to use a very simple summary. So these density estimates, even the quantile plot to some extent, they're all displaying as much of the data as you can. But when you're just trying to do a very quick comparison of many different distributions or many different samples, it's really helpful to reduce the amount of data you're displaying. Using a box plot, for example, and then an Eulerian path to compare things in a particular way is the best way to do it, in my opinion. So let's quickly go over what we have. We did this univariate journey to introduce all of these candidate visual estimators. We now have, as well, a few different candidate ways of comparing visual estimates. And of course, you're free to come up with any other way you might want to. Like it is a very creative act to say, oh, I want to put this density rotated 90 degrees with that density rotated 90 degrees with another one and compare some weird box shape. But these are 2 parts of a hypothesis test. You have an estimator, and you have some metric to compare the 2 estimates you get using that estimator on 2 different samples. All we need now is a null hypothesis and a null distribution. And then we would have everything we need for a significance test. So if we consider the fact we have 2 samples, we let the distribution of the first one be F1, the distribution of the second be F2. In our example, the mountain heights in Switzerland and Norway, or Norway and Switzerland, respectively. This is our null hypothesis. These 2 have the same distribution. But what is the distribution of our visual estimate under this null? You can't just say like, oh, the mean of a difference, if the sample size is large enough, is going to tend to a normal distribution, because we're dealing with something that you actually visually look at. It's not even clear how you would put something like a normal distribution around this. What we do to account for this is actually what the original statisticians always wanted to do. You can, if you ever are as much of a nerd as me, go back and read the papers from the early 1900s. Guys like Fisher, Pearson, Ewell, they desperately wanted to be able to simulate how things actually behaved when you did multiple samples. But this was before computers. So the best thing you could do would be to roll a dice 10,000 times. There's some really unique ways with spinners they tried to do stuff. There used to be people who would look at the roulette numbers from casinos reported in the newspaper and record all of them for a long period of time to try and simulate random draws. They really wanted to be able to simulate, but because they didn't have computers, it was infeasible. It would take days to collect thousands of observations, and it would be days of doing the same boring, repetitive task over and over and over again. There's actually a really interesting story about, I think it might have been a prisoner of war in World War II, who flipped a coin and recorded tens of thousands of coin flips in this one really long run while he was a prisoner of war. because I guess he wanted something to do. But that gives you some idea of how fun this is, and that he was a prisoner and it was the best thing he could do. So the idea behind this is that we've seen some differences when we look at a distribution. Have two of them plotted side by side. We'd like to simulate, under the fact they're equal, how likely these differences actually are. We don't want to get too excited over something which is just random chance. So under the null hypothesis, we have these two samples. If they're both from the same distribution, they're all independent estimates, or all independent observations. Wrong term there. We can just mix these two samples however we like and split them up again. If we do that, because they're all independent observations from the same distribution, it shouldn't change the distribution of either of the two samples. They should look basically the same. So why don't we try that and see what it looks like? So I have here something which mixes the peaks together. I then do a sampling of the indices. You do not want to replace. I believe replace equals false is the default. But you don't want to replace in this because you can't have the same peak appearing in two different data sets. They all are unique observations. And then, once you've selected the indices, you can use negative indexing to really conveniently create one sample and the other sample. And then you can just do a simple back-to-back density estimate. Now, I don't know how well you remember the original plot, so we put them side by side. And this is the fundamental idea of what we're trying to do. We're just trying to compare what we've seen to what happens by chance. The only thing is, just one example isn't enough to build anything like a p-value. So Fisher's classic thing was, the ability of, I think it was a lady, to detect whether milk or tea was added to a cup first. And if she got it right once, I don't think anyone would be convinced that she actually knows what she's doing. So you'd want to do it multiple times, and then figure out the likelihood that she got it right all of those times if she were just guessing 50-50. And this is exactly what we do here. It's the same concept. This lineup test introduced in the lectures is the idea that we simulate multiple times, we hide the true display somewhere in the data, and then the point is, if you can correctly identify where that is, given that you don't know what these samples look like, there's an indication there might be something going on. And this is actually the topic of the statistical inference for exploratory data analysis paper by Buja. It's the idea of the lineup test in the class is if we do this multiple times, if we build a nice grid and point out the true suspect, as it were, we can actually build a p-value into this, even though at first we don't actually know what the null distribution is. So we're using this simulation and an analyst, someone looking at this, to build a p-value very naturally. And it's based off of, simple binomial probability. We only have 5 minutes left, so I'm just going to go through a quick summary of what we've talked about, kind of a broad view of these last few weeks as well of the class. So whenever we're trying to visualize a distribution, we're going to display certain features. Every single one of these visuals is an estimator, which we're applying to the data to gain some insight into aspects of the distribution. Of course, every estimator has some sort of bias and variance to it. They all have their own little quirks. So for example, a histogram is never going to follow the data perfectly, whereas something like a quantile plot is going to pick up even the slightest change in any one of the points, which may distract from other patterns in the data or the broad pattern overall. Think about the really long right tail in our particular example, which hid some of those smaller modes in the peak heights. They all come with a different level of complexity. Just like a numerical estimator. Doing something like the mean is way easier than a linear model which takes into account confounders. There's a different level of complexity there. And similarly, with visual estimators, you can build in more complexity if you want to. And the only difference here that makes it different than other estimators is that aesthetics and familiarity for the viewer are kind of key things to consider here. In my opinion, at least, displaying really bad visuals just detracts from the point of using them in the first place. You want to think carefully about them, you want to edit them, go over them multiple times and make slight tweaks just to make it look a little bit better and easier for a viewer to see what you're talking about. But comparing these visual estimates, unlike numerical estimates, requires a lot of creativity. There's a lot of different options. Each has its own benefits and drawbacks. And certain visual estimators are going to work best with certain comparison methods. This isn't actually too different than something like numerical estimates. Ratios work better in some cases, differences work better in others. And by using simulation, we can generate a whole bunch of candidates to determine what the null distribution of our visual estimator is, despite not knowing what the distribution of the data actually is. It's non-parametric, but we still get a p-value in the end. There's some drawbacks to using a lineup test. I believe they're discussed in the slides. Things like the fatigue of if you wanted to get a really small p-value, you need to display hundreds of plots, and the analyst may just lose interest partway through. But yeah, that's the whole presentation. That's today's tutorial. If you have any questions, feel free to come up. Otherwise, have a great week. All the best with the assignment, and enjoy reading week 2. That's next week, eh?